Today, we're going to trace the incredible life of a star, from its very first flicker in some distant cosmic nursery, all the way to its final, universe-shaping explosion. It's a story of creation and of destruction, on a scale that is just almost impossible to wrap your head around.
I mean, really, have you? Because they're not just these peaceful, twinkling little lights. Nope. Every single star up there is a raging battlefield. That's a constant, furious war between gravity trying to crush it and a massive internal furnace trying to blow it apart. And you know what? Understanding that battle, that's the key to understanding, well, pretty much the entire universe.
So what is a star? Really? At its heart, it's this massive, brilliant ball of plasma that's held together by a perfect, almost impossibly delicate balance. It's an epic tug-of-war that can last for billions and billions of years.
Now, there's a cool name for this. It's called hydrostatic equilibrium. On one side, you have the absolutely immense force of gravity, always trying to collapse the star into a single tiny point. And pushing back against that is this incredible outward pressure from the sheer energy being created in the core. This perfect standoff is what keeps a star stable for its entire life. And where does all that energy come from? Well, it's a process called nuclear fusion. Deep inside the star's core, where the temperatures and pressures are just insane, hydrogen atoms are getting slammed together so hard that they fuse and create helium. And in that process, a tiny, tiny fraction of their mass gets inverted directly into a huge amount of energy. That's it. That's the engine that makes a star shine. So the star just keeps on fusing heavier and heavier elements. It's like a cosmic factory, turning helium into carbon, carbon into oxygen, and so on down the line. But that production line, it hits a wall. And that wall is iron. You see, fusing all the elements up to iron releases energy. But when you try to fuse iron, it actually consumes energy. It's basically the final ash in the stellar furnace. And when that iron ash starts to build up, the star's engine begins to die.
Okay, so this all sounds great, but how on earth do we know any of this? It's not like we can fly a spaceship to a star and take a sample, right? Well, the answer is actually hidden in the starlight itself. By breaking down that light into its rainbow of colors, a technique we call spectroscopy, we get this kind of cosmic Rosetta Stone that lets us read a star's deepest secrets from billions of miles away.
Think of it like a cosmic barcode. The star's superhot core pumps out a full, continuous rainbow of light. But as that light travels out through the star's cooler atmosphere, the different elements in that atmosphere, like hydrogen or helium, absorb their own very specific signature colors. This leaves little black lines in the rainbow. By analyzing those missing lines, that barcode, we can tell exactly what a star is made of, how hot it is, and even how dense it is. It's amazing.
All right, now that we know how we know this stuff, let's rewind the clock, way back, to the very beginning. Where do stars even come from? Well, their story doesn't start with a bang, but with a slow, quiet, cold collapse in the unbelievable vastness of space. It all kicks off inside what's called a giant molecular cloud, just this enormous, dark expanse of gas and dust. Over thousands of years, gravity starts to win, pulling the densest clumps together. After about 100,000 years, you get a hot, dense core, called a protostar. For the next 10 million years or so, it just keeps pulling in more material, getting hotter and hotter, until its core finally hits a blistering 8 million Kelvin. At that exact moment, poof, fusion ignites. A star is officially born.
Okay, so the star is born, the chaotic part is over, and now it settles in for the long haul. This phase is called the main sequence, and it's where a star will spend about 90% of its life, just steadily fusing hydrogen into helium. But not all main sequence stars are created equal. Not at all.
Astronomers classify stars by their temperature using this sequence you see here, O, B, A, F, G, K, M. The O stars are the hottest and most massive. They burn a brilliant blue and live incredibly fast, violent lives. Way down at the other end, you have the M stars. They're much smaller, cooler, and glow a faint red, sipping their fuel so slowly they can last for trillions of years. And our Sun? It's a G-class star, kind of like the Goldilocks of stars, right in that comfortable, stable yellow zone.
Now, trying to remember O, B, A, F, G, K, M could be a bit tricky. So for generations, astronomers have used this classic little memory trick. O, be a fine girl, kiss me. It's a little quirky, for sure, but hey, it works.
And just to give you an idea of the sheer power we're talking about, at the extreme end of that scale, get this. The most luminous star we've ever found is called RMC 136A1.
It shines with the light of 8.7 million of our suns. It's a true stellar monster. The amount of energy it puts out in just 5 seconds is more than our sun produces in an entire year. That's just mind-boggling.
But, like all good things, this long, stable life of burning hydrogen can't go on forever. Eventually, the fuel in the core starts to run low, and that's when the star enters its final dramatic act, and the story takes a much more violent turn. So what happens when that hydrogen tank in the core finally starts to run on empty? Well, that delicate balance between gravity and fusion, it's broken. Gravity immediately starts to take over, the core shrinks and heats up, and the star's fate is sealed. But how it dies, that all comes down to one single thing: its mass. And this is where the story literally splits into 2 completely different paths. For stars up to about 8 times the mass of our sun, the end is, relatively peaceful. But for the true giants of the universe, their end is one of the most violent and spectacular events in the entire cosmos.
So, for a star like our sun, as its core runs out of fuel and contracts, its outer layers swell up, turning it into a massive red giant. Eventually, those outer layers just kinda drift away into space, creating one of the most beautiful objects in the cosmos, a glowing structure we call a planetary nebula. And all that's left behind is the star's dead core, an incredibly dense Earth-sized ember called a white dwarf.
Okay, so that's the gentle path. For the real cosmic heavyweights, the end is, well, it's anything but gentle. When they run out of fuel, they don't just fade away. They go out with a bang that can literally outshine its entire home galaxy.
Here's how it happens, and it happens fast. The star forges an onion-like core of heavier and heavier elements until it hits iron. The fusion engine stops. Dead stop. With no outward pressure, gravity wins. Instantly. The core collapses in less than a second, then violently rebounds in a cataclysmic explosion that we call a supernova.
But a supernova isn't just an ending, it's a profound act of creation. That explosion is so powerful it forges all the elements heavier than iron. We're talking the gold in your jewelry, the silver in your coins, the calcium in your bones, and it scatters them across the galaxy. This star stuff becomes the raw material for the next generation of stars, planets, and even us.
And what's left behind after all that chaos? Well, it depends on how big the star was to begin with, but you get one of 2 of the most extreme objects in the universe. You might get a neutron star, an object the size of a city but with more mass than our sun packed inside. A single teaspoon of it would weigh billions of tons. Or, if the star was truly massive, the core collapses completely into a black hole, a point in space-time where gravity is so strong that absolutely nothing, not even light, can escape. And speaking of massive, the biggest star we know of in terms of sheer size is Stephenson 218. It is a staggering 2,150 times the radius of our sun. Let me put that another way. If you swapped our sun with this thing, its surface would stretch out past Jupiter, past Saturn, all the way to the orbit of Uranus. Just try to picture that.
And this all brings us back to something really profound, a thought that Carl Sagan captured so perfectly. The iron in our blood, the oxygen we breathe, the carbon that makes up our bodies, every single atom was forged in the heart of a massive star that lived and died billions of years ago. We are, quite literally, made of star stuff. And so that really leaves us with one final thought. We are all part of this incredible, grand, cosmic cycle of birth, death, and rebirth. So if we're made from the ashes of stars that died long ago, it really makes you wonder, doesn't it? What amazing new things will be built from the stars that are dying all across the universe right now?